As an example of how to think of surface tension as a force per exposed line distance, um, one of the most important applications for this is trying to understand why the internal pressure inside of a droplet is higher than the external air or whatever the vapor is. So to do that, imagine taking a spherical droplet and doing a force balance. So what I'll do is I'll just I'll cut the droplet in half, and I'll just look at a force balance between the surface tension forces acting on the outer perimeter and the pressure that must be building up inside to counter that surface tension force that's on the outside. So the surface tension force is equal to 2 pi r times the surface tension. That's 2 pi r is the perimeter, the outer perimeter of a circle, and the surface tension tells you how much force there is. That has to be counterbalanced in equilibrium by an internal pressure. I'll call the difference between the external and the internal pressure delta P, and in equilibrium, those two forces must balance one another. Given that the area inside the sphere is pi r squared, you can set those two internal, the pressure forces equal to the surface tension forces, and after doing just a little bit of cancellation, you can show that the change in pressure, or the internal pressure inside the droplet, must be equal to 2 times the surface tension divided by the radius of the droplet, meaning that the smaller the radius of the droplet is, the higher the internal pressure is. So very small droplets come with a very significant pressure buildup on the inside of them. We can do the same sort of equilibrium balance for a bubble. The difference between a bubble and a droplet is that a bubble has a very thin shell of liquid, and then inside that liquid there's another vapor. So there's twice as many surfaces in a thin bubble. So the only real difference is, in terms of doing this force balance for a droplet and a bubble, is that there's twice as much perimeter for the surface tension to act on. So the force, the internal force due to surface tension pulling on the bubble, is twice as big. So 2 times 2 pi r times the surface tension sigma. And then if we do a force balance where the internal pressure has to counteract that surface tension force, then you find out that basically the internal pressure is twice as big. So 4 times sigma divided by r. And again, the smaller the bubble is, the more internal pressure has to exist to counteract the surface tension that's pulling on everything.